Welcome to Transmathematica. I'm James Anderson. Today I'm going to talk about the empty symbol and logical division by zero. I'm going to show you how to divide by zero using logic. When we're doing arithmetic and we come across nothing, we don't give up, we calculate using zero. And the same is true of logic. When we come across something that's undefined, we don't give up, we calculate using the empty symbol epsilon. And I'm going to show you how to use the logical symbol epsilon to divide by zero. That's a logical method of dividing by zero. And once we can divide by zero using logic, I'll show you how to extend that to many different ways of dividing by zero using arithmetic. Now there is some mathematical background to this, but don't worry. I've got post-it notes and cookies to explain what's going on. I'll be using the properties of an algebraic structure called a field. A field is a set together with two operations on the set called addition and multiplication. If you know what a field is, that's great. If you don't know what a field is, that's okay. In school you learned arithmetic, and arithmetic is made up of a set of numbers and the two operations addition and multiplication. Now many people mistakenly believe that division by zero is impossible, and they mistakenly believe they can prove that using fields. But take a close look. A field has just two operations, addition and multiplication. It doesn't have an operation of subtraction, it doesn't have division. So we're not going to be able to prove that division by zero is impossible because we don't have division. And even if we add division to a field, there are many ways of adding it, and some of those do allow division by zero. This is the most popular way of adding division to a field. We say that a divided by b equals a times b to the power minus 1. A field doesn't have division, but it does have multiplication. We've translated division into multiplication. Now in logic, you can replace the variables a and b by any values at all. We can replace a and b by any numbers at all. For example, we can replace b by 0, and then we get a divided by 0 equals a times 0 to the power minus 1. The axiom a divided by b equals a times b to the power minus 1 brings into existence division by 0. And it brings into existence 0 to the power minus 1. These things exist because the logic says they do. Now, if you believe that division by 0 is impossible, or you believe that 0 to the power minus 1 doesn't exist, then you are mistaken. You are mistaken about logic, and that has a consequence. It means you're mistaken about every science. So it's a big deal. If we're going to understand division by zero logically, then we need to know what the properties of 0 to the power minus 1 are. So let's explore, find some properties, let's find some pieces of the jigsaw puzzle and see if we can put them together into a meaningful picture. As usual, I'm going to define something called the multiplicative inverse, and I do that with an axiom. When b is not equal to 0, it's the case that b to the power minus 1 is a solution of b times b to the power minus 1 equals 1, in which case b to the power minus 1 is called the multiplicative inverse of b. So my question is, what is 0 to the power minus 1? If you don't know, then you have misunderstood logic. Let's explore another property of the power minus 1. When b is not equal to 0, it is the case that b to the power minus 1 is unique. Given a non-zero number b, there is only one number b to the power minus 1, such that b times b to the power minus 1 equals 1. Here's a proof. We start by saying let b be an arbitrary non-zero number. The proof is stated in terms of the variable b, but by choosing b arbitrarily, by letting b be any number at all other than 0, then we're proving the theorem for every number other than 0. So next, let c and d be arbitrary multiplicative inverses of b, such that b times c equals 1 and b times d equals 1. What that means is we're supposing that there could be lots of multiplicative inverses, C, D, E, F, G, whatever, and we're about to prove that they're all the same. In other words, that the multiplicative inverse is unique. Give me a number like 2, and I'll give you back the only multiplicative inverse, 1 over 2, 1/2. Now the proof gives the big picture. We're now going to take care of the details in a lemma. This sounds a bit technical, but if you're a programmer, think of the proof as a program, think of the lemma as a subroutine. In the proof, we let b times c equals 1, we let b times d equals 1. Now we're going to import those as variables to our subroutine, and we say, given that b times c equals 1, that was already given by the proof, given that b times d equals 1, that was already given by the proof, then c is equal to d. And how do we prove this? Well, we start off by saying something true. We start off by saying that c equals c times 1. This is true because any number times 1 is equal to itself. And we know that 1 equals b times d. Arithmetic is associative, so we know that c times the product of b and d is equal to the product of c and b times d. Arithmetic is commutative, so c times b equals b times c. We know that b times c equals 1. 1 times any number is equal to that number, and so we've proved that c equals d. So now we know the multiplicative inverse is unique, and we write down when b is not equal to 0, it is the case that b to the power minus 1 is the unique multiplicative inverse of b. So my question is, when b equals 0, what is 0 to the power minus 1? Well, let's explore some more properties of 0 to the power minus 1. The condition b not equal to 0 is necessary to the solution of b times b to the power minus 1 equals 1. If instead we allowed 0 to have a multiplicative inverse, then 0 times 0 to the power minus 1 equals 1, but this leads to a contradiction. We start off by assuming that 1 equals 0 times 0 to the power minus 1, but 0 times anything equals 0, and so we get the contradiction 1 equals 0. As we can't have a contradiction, it proves that it's necessarily the case that 0 to the power minus 1 is not the multiplicative inverse of 0. And that means it's impossible to use the multiplicative inverse to prove that division by 0 is impossible, because a divided by 0 equals a times 0 to the power minus 1, and we've just proved that 0 to the power minus 1 is not the multiplicative inverse of 0. The multiplicative inverse is irrelevant to division by 0. If you thought otherwise, you are mistaken, and you've misunderstood the field axioms. As a consequence, you misunderstand arithmetic, calculus, physics, and all of the numerical sciences. Now, this question of what is 0 to the power minus 1 has been debated in different forms for over 1,500 years, and there are a number of different answers. I'm going to concentrate on the answers that have been given in the last 150 years. The first answer, when b equals 0, what is b to the power minus 1? In other words, what is 0 to the power minus 1 is to say that 0 to the power minus 1 is undefined. Now, saying that 0 to the power minus 1 is undefined is a good answer. It identifies 0 to the power minus 1 as belonging to a class of things that are undefined. But we shouldn't stop processing undefined things. If we do that, then logic fails, and that's bad. What we should do is carry on using logic. Now, another answer to the question, what is 0 to the power minus 1, is to say that 0 to the power minus 1 is an unanalyzed symbol such that 0 to the power minus 1 equals 0 to the power minus 1. And this is a much more insightful answer than it looks at first glance. If you look at the slide, you'll see I've written 0 to the power minus 1 inside quotation marks. And this is to show that it's a single symbol. It doesn't break up into 0 and the power minus 1. It just is the single symbol 0 to the power minus 1 all glued together as one thing. We can't analyse the symbol into its parts. But we can do quite a lot with an unanalyzed symbol. For example, we know that 0 to the power minus 1 is not equal to 0 to the power minus 1 plus 1 because the symbols are different. But we do know that 0 to the power minus 1 plus 1 is equal to 0 to the power minus 1 plus 1 because the symbols are the same. We know that 0 to the power minus 1 plus 1 plus 1 is not equal to 0 to the power minus 1 plus 2, but we can work out that 0 to the power minus 1 plus 1 plus 1 transforms into 0 to the power minus 1 plus 2, because we can do the arithmetic, 1 plus 1 equals 2. And now we know that 0 to the power minus 1 plus 2 equals 0 to the power minus 1 plus 2. We can recreate the whole of arithmetic despite the fact that 0 to the power minus 1 is an unanalyzed symbol. Now this seems strange to logicians, but it's much more common in computer science. People who write compilers are completely happy with the idea of processing unanalyzed symbols. Now a third answer to the question what is 0 to the power minus 1 is my favourite answer. It's 0 to the power minus 1 is the unique empty symbol epsilon. Choose any number for b. It doesn't matter if it's 0 or not. If b is non-zero, then b to the power minus 1 is uniquely defined as the multiplicative inverse, but if b is 0, then 0 to the power minus 1 is the unique empty symbol epsilon. In both cases, b to the power minus 1 is defined uniquely. We've done a lot of mathematics. Now let's have some fun and use post-it notes to explain what's going on. I've put 3 on the plate. Now I take off whatever's on the plate and put down a new number, which is its multiplicative inverse. 1/3 times 3 equals 1. Let's suppose that 1/3 is on the plate. I take whatever's on the plate off and I put on the plate a number which is its multiplicative inverse. 3 times 1/3 equals 1. Let's try a smaller number 2. I take whatever's on the plate off and I put its multiplicative inverse on the plate, 1/2, because 2 times 1/2 equals 1. Suppose 1/2 is on the plate, I take it off, I put its multiplicative inverse on the plate, 2 times 1/2 equals 1. Let's make the number smaller. I put 1 on the plate, I take whatever's on the plate off, I put its multiplicative inverse on the plate, and I've got 1, because 1 times 1 equals 1. Let's make it smaller. I put 0 on the plate, I take it off, and my logical rules don't tell me what the inverse is. So when I put the answer back, I've put nothing on the plate. Suppose there is nothing on the plate. Then I know how to raise it to the power minus 1 because there's only one number that leaves nothing on the plate, and that is 0. So we can see that given any number b, we can calculate b to the power minus 1. It's maybe even more obvious if we use cookies. Here I've got 3 cookies. I take them off and I put its multiplicative inverse, 1/3 of a cookie, on the plate. Suppose there's 1/3 of a cookie on the plate, I take it off and put its multiplicative inverse, 1, 2, 3 cookies on the plate. Suppose I've only got 2 cookies on the plate. I take them off and I put their multiplicative inverse, half a cookie, on the plate. Suppose I've got only half a cookie, I take it off and put its multiplicative inverse, 2 cookies, on the plate. Suppose I've only got 1 cookie. I take it off, I put its multiplicative inverse, 1 cookie, on the plate. Suppose I've got no cookies on the plate. I can't calculate the multiplicative inverse of 0 cookies, but I can calculate 0 to the power minus 1. This is how I do it. There is nothing on the plate. I take it off. The logic doesn't tell me what 0 to the power minus 1 is, so I obey the logic. I don't put anything back on the plate. When I've finished what's on the plate's empty. What's on the plate is the empty symbol when we're doing logic, and it's the number 0 when we're dealing with cookies. So the empty symbol and 0 are the same thing. They're the absence of everything. Because the mapping from b to the power minus 1 is unique, the inverse mapping from b to the power minus 1 to b is unique, such that, and this looks a little bit weird, nothing at all raised to the power minus 1 equals epsilon to the power minus 1 equals 0. Now when I write nothing at all to the power minus 1, that's a badly formed formula. Logicians usually don't like badly formed formulas, but we can make it well formed by replacing the nothing at all with epsilon. So epsilon is the empty symbol. It stands for nothing at all. It is replaced by nothing at all. The idea of epsilon comes from computer science. It's used in compilers. If you're a logician, if you're a mathematician, you're going to love compilers. Compilers write end-user programs, which are basically theorems and lemmas. The theorems are the programs, the subroutines are the lemmas. Now the code inside the compiler is a program and some subroutines. It's a meta-theorem and some meta-lemmas. Now you don't normally just write a compiler, you write it in a language and use a compiler to make the compiler. So what you write in the compiler is a meta-meta theorem and a meta-meta lemma. And there's some theory about how you write compilers, and that uses meta-meta-meta theorems and meta-meta-meta lemmas. You will absolutely love it. So now we've come to the crucial part of the story, epsilon totalization. When an undefined value arises in a logical description, the description is partial. It fails in some way. An undefined value can be replaced by the empty symbol known as epsilon in a process I call epsilon totalization. An epsilon totalization is the backstop totalization. It always works. It's a total method for totalizing things. So now we've worked out how to divide by 0 using logic, using the empty symbol. And that applies in the real world. We can divide numbers on a plate. We can divide cookies. But it would be nice to be able to do things with arithmetic, not just with logic. And we can do that in several ways. We can substitute any symbol for epsilon that doesn't contradict the field axioms. In other words, we can replace epsilon with anything that doesn't contradict the rules of arithmetic. And one example is to take epsilon to the power 0 minus 1 equals 0. And that's called the Suppes-Ono axiom. It extends every field so it supports division by 0. Now there's a lot to unpack in that sentence. When we say that the field axioms are extended, we mean that any new objects obey all of the existing laws of a field. For example, 0. 0 is already an element of the field. 0 is already a number in arithmetic. Taking 0 to the power minus 1 equals 0 preserves all of the laws of arithmetic and of fields. The Suppes-Ono axiom is named after two people. Patrick Suppes was a philosopher in the United States. He wanted to prove that physics is consistent. I'll make another video about him. And he came across the solution 0 to the power minus 1 equals 0. Ono is a Japanese mathematician. You can track him down and email him if you speak Japanese. Now, we don't have to extend axioms. We can instead augment them. Augmenting means we add something to a field, but what we add doesn't have to obey all of the existing rules. We're creating some new kind of structure. We're creating an augmented structure. The second example is that we choose epsilon equals 0 to the power minus 1 and replace it with bottom. And lots of different kinds of division by 0 use bottom. As a third example, we can choose epsilon equals 0 to the power minus 1. We can replace 0 with 0 over 1 and then say that 0 over 1 to the power minus 1 equals 1 over 0 is equal to infinity. Look closely at 0 over 1 and 1 over 0. 1 over 0 is the lexical reciprocal of 0 over 1. Take 0 over 1 and turn it upside down and you get 1 over 0. But 0 over 1 is not the reciprocal of 1 over 0. Mathematicians are very careful to define the reciprocal so that it does not allow division by 0. For the last 150 years or thereabouts, mathematicians have been committed to preventing division by 0. And that guarantees failure in arithmetic. It guarantees failure in calculus, in physics, in all of the numerate sciences. I understand why mathematicians have done it that way, but I think it's a bad idea. You can take any field and augment it to provide division by 0 in these two ways. And we can do more. We can add more than one element. For example, we can add minus infinity equals minus 1 over 0, nullity equals 0 over 0, and infinity equals 1 over 0. And we could add yet more. We could take minus infinity, nullity, infinity, and bottom. And we could do even more. There's no end to how many things we could do. So in conclusion then, 0 to the power minus 1 equals. If you find that statement difficult to understand, then watch the video again. If you get back to here and you still don't understand it, take a break. Get on with the rest of your life and pop back every now and then and see if you understand it. Another way of saying 0 to the power minus 1 equals is to say 0 to the power minus 1 equals epsilon. And the moral is, if you cannot read what is not written, then you are guaranteed to fail. Subscribe to Transmathematica for more.